So I wanted to honor the invitation to come speak here by just giving a sense of what kinds of work or what kind of research can be done in a kind of philosophy department, a specific type of philosophy department in the United States. Not that it doesn't happen elsewhere, but I know that there's a lot presupposed in any discussion, and I wanted to just sort of cover the basics so that even people with no background whatsoever might just get a sense of what's interesting to me about this kind of area, mathematical logic and the philosophy of mathematics, and maybe just inspire some of you to pursue it a little bit if you find it interesting. But before I get started, so this is a club based on, is it mostly Buddhist philosophy that you read? Am I right in that? Or what's the kind of topic? No? Am I already off? All kinds of topics? Okay. Oh, okay. So maybe I'm not totally off in yeah. So let's just get started by thinking about what it is that some philosophers care about. So some philosophers care about truth, right? They care about what's true. And for many people, there are certain statements that seem importantly true in this special respect, which is that they're true all the time, no matter what else is happening. So some truths vary, right? Like, I am wearing a sweater, right? That's not always true. It's true today, but it would be false yesterday. But what's an example of something that's always true, no matter when you say it? Does anyone have an idea? Have an example they can think of? Okay, the sun rises in the east, but even that could possibly become false. It would be weird, right? But what if there was a shift in the solar system? Then we would just say, yeah, the sun does not rise in the east anymore, right? That's possible, okay? So it's an example of something we take to be true, and there's no problem calling it true, but it's still not absolutely true. So what's an example of something that's always true no matter what? Yeah, the Pythagorean theorem, for example. Any other examples? Can you think of any? I bet you're thinking of mathematical examples though, right? 2 + 2 = 4. That's always true, right? It's not going to become false tomorrow or anytime, okay? Now here's the big question. Why is 2 + 2 = 4 always true? Okay? You presumably all know that 2 + 2 = 4, but you probably never asked why, okay? So that's where the discussion takes place. And I'll start now outlining a bit of the history of mathematics that has led up to attempts to answer this question by philosophers. So, it's been long recognized that mathematics occupies this special place of being always true, or timelessly or universally true. Ancient philosophers like Plato recognized this, Aristotle, and it was considered part of the philosophy of mathematics to explain this fact. So Plato thought that mathematical objects exist in this timeless realm, the Platonic realm, and they were similar to what he also considered to be timeless entities called the forms. And so the reason that 2 + 2 = 4, according to Plato, is because out there in the Platonic realm, there is the number 2. And if you add the number 2 to itself, the number 2, you get the number 4 with this other entity out there in the Platonic realm. So that's crazy, right? That's crazy. Of course there aren't these numbers out there, right? That's just, nobody needs to invent this other universe just to make sense of it. We should look for other better accounts, theories of the truth of mathematics. So are you kind of maybe thinking what options there are for explaining it? Okay, so I'm going to now introduce some terminology that helps capture what's unique about mathematical truths. So the example that Sun gave, the sun always rises in the east, that is a truth about the world, right? It's about the physical universe we inhabit. And we can say that it's true now. We know it's true. But to know that it's true, we know that based off of experience, based off of observation. We go out and we see the sun always rising, right? And we find out that it's true. And now maybe a better example of a universal but still physical truth is like Einstein's law, E equals mc squared, all right? That's not likely to become false anytime soon. The sun could conceivably stop rising in the east if like an asteroid impacted Earth, but E equals mc squared is not going to become false anytime soon. Still, we don't just invent the truth E equals mc squared independently of observation. We observe energy and we observe mass and we come to figure out that it's true. And so this is called a synthetic truth. Now a synthetic just is a terminological, it's a point of terminology that means it's true based off of it's an a posteriori truth. So it's based on observation. So I introduced this terminology, a posteriori, that's the Latin phrase, and it just means true because of observation or experience. Now, there is another kind of truth, and it's called a priori. And this is true not based off of observation, but based off of something else. Yeah. Logic. Logic or meaning. So here's an example of an a priori truth. It's an example from the English language, but I hope that it'll still have impact. All bachelors are male. Okay? You know what a bachelor is? What is a bachelor? It's an unmarried male, right? So to say that all bachelors are male it's true and it'll always be true, right? But that's just because of the meaning of the terms. So that's an example of an a priori truth. Now that we have these two kinds, a posteriori and a priori, what kind do you think mathematical truths might be? Right. So many people now will say that mathematical truths are a priori and that they're true independent of our experience. To put it this way, even if you had never seen the world, if all your senses were dulled, you could have no contact with the external world, you would still be able to figure out that 2 + 2 = 4, right? It doesn't depend on observation, okay? Now there's one philosopher who tried to make the case that mathematical truths actually are a posteriori instead of a priori, and that was Mill, John Stuart Mill. Have you heard of him? Okay. He tried to argue that even statements like 2 + 2 = 4 are generalizations of observations. So we come to know 2 + 2 = 4 by observing lots of times that we took two things, put two more things there, and saw that there were four things. And he says, okay, so we actually acquire knowledge of mathematics through experience. That might be plausible or that might seem to work for easy statements like 2 + 2 = 4. But when you get into really, really big numbers or other parts of mathematics, like 1,02,700 plus 2,600,700 equals, some number z, then it doesn't seem like our experience is going to be what tells us that that's true, even though we still have absolute certainty that whatever that statement is, that it's true, right? Well, we know for sure that that's going to be true. So, we've arrived at this idea that mathematical statements are a priori. They're true independent of experience. That's going to be one of the keys in the direction towards Logicism, which is where this talk is headed, okay? Now the other direction, or the other strand of history that we're going to now talk about is that as mathematics developed, especially in the 17th and 18th centuries, mostly by French, British, and German mathematicians, Leibniz, Newton, Laplace, these types of people, they invented calculus. They invented these super powerful mathematical theories, and the theories worked. They allowed us to predict the movement of heavenly bodies. They allowed us to do all these more complicated calculations that could not have been done before. But in order to do the mathematics, Leibniz in particular introduced the concept of an infinitesimal, which is, have you ever done calculus? Anyone have studied calculus? You remember if you write like f of x and then dx, the little dx, and did they tell you that those are called infinitesimals? And what are those supposed to be? They're supposed to be infinitely small, right? Infinitely small numbers, or something like that. Now, you can debate about how important this is to using calculus, but it looked like mathematicians were appealing to these weird entities, infinitely small numbers, and then Newton himself had this notion of a fluxion. So there were these really weird concepts, and the big problem was that we didn't know what to make of these concepts, and so instead of relying on them, we wanted to put the new mathematics, like calculus, on a more solid foundation. So we wanted to come up with a new theory that helped explain why it was so successful. And this was accomplished in the 19th century. So this was a great project. It was called the reduction of analysis to arithmetic. Analysis being calculus, okay? So calculus, we found a way where we gave new foundations for it, where suddenly you didn't have to appeal to things like dx or infinitely small numbers or fluxions. You instead did it all in terms of a new logic, a new logical terminology. I won't get into the details. I couldn't even tell you if I wanted to. It's hard. I'm not ready for it right now. But the point is that now we felt really confident that calculus didn't just work, but it was actually true. It was it had the same truth status as arithmetic, because just using arithmetic, you can derive everything in analysis and calculus, okay? So this is basically part of a general project of reductionism, reducing higher theories to lower theories, reducing what isn't certain to things that are certain, okay? Now take arithmetic. We've already gone from analysis to arithmetic. What about arithmetic? To something more certain? So this is now where the Logicism comes in, okay? Logicism is a theory about mathematics. And because everything else in mathematics has been reduced to arithmetic, you can say it's just in terms of arithmetic. And here's the theory. Arithmetic can be reduced just to logic. That's all you need. From a few principles of logic, you can derive arithmetic. And then, since everything else derives from arithmetic, that means that all mathematics is just logic. Okay? Now, does that seem obvious? No? Okay, now, I know that I'm just throwing the word logic out there, and you're not sure exactly what I mean when I say it can be reduced to logic. So I'm not going to have enough time in this short talk to show you what kinds of logics what kind of truths you're able to rely on here to get arithmetic. But I will be able to say that there is one philosopher who carried out the Logicism project almost to completion before it fell apart on him. And his name was Gottlob Frege, F-R-E-G-E. He was a German mathematician, and he was working in the late 19th century. His work started in about 1875, 1876, and he was publishing his work in the 1880s and such, in the 1890s, and he became very obsessed with this idea that we should be able to reduce arithmetic to logic. And although there is a mathematical part of the project, just like how when we reduced analysis to arithmetic, that was mostly mathematical, there's also a philosophical aspect of the project. Because what do we think the truths of logic are? Let me give you an example. P, where P stands for some sentence, okay? P or not P. So here's an example. It is raining or it is not raining, okay? What kind of statement is that? Is that true? Let's just, for the sake of argument, agree that it's true, okay? It's raining or it's not raining, okay? For any statement P, I can put any statement in there, and that kind of sentence will still be true, right? Okay? The sky is blue or the sky is not blue. Whatever, right? It's always going to be true, okay? So what kind of statement do we think those types are? Are they a posteriori or a priori? Are they based on observing the world, or are they based independently of observing the world, based on their meaning instead? Okay, who thinks they're a priori? Who thinks they're true just in virtue of their meaning, not by observing the world? Do I have to go look at the sky to tell you whether this statement is true? The sky is blue or the sky is not blue. I don't have to go look at the world, right? I just know that. Doesn't even matter what sentence I put in there. It's a priori. We know it independently of observation. So, that's what the truths of logic are. They're a priori. Now, if we have that logic is a priori, and that from logic we can derive arithmetic, then what does arithmetic become? It also becomes a priori. And we want that already, right? We already gave an argument or a sort of intuition for why arithmetic should be a priori. So if arithmetic was merely logic, then that would satisfy all these philosophers about what mathematical truths really are and why they're true. Okay? So Frege set out to prove this thesis. He wrote a few books. He was pretty much working by himself. Nobody else was interested in this. Everyone thought he was just this weirdo for doing what he's doing, you know. And he's a mathematician. All the other mathematicians are working on other stuff, and he just cares about this weird philosophical thing none of the other mathematicians quite are as interested in. But he pursues it with all his force, and he dedicates his life to it. And for him, this is so important. Mathematics is so important, right? It is our example of certainty, and we really want it to be true, and we want to believe in it. So he thought that he's giving us the best reason for believing in it. This is like the grounds for our belief. You know how important it is to have justification for things you take to be true, right? If someone says, God exists, you want to ask, why? Why do you believe that, right? These kinds of examples. If someone says 2 + 2 = 4, you might not have thought it, but you should still ask, why? Why is that true, right? So you should always be asking that question, why is it true? Okay? Sadly, Frege did not manage to establish his thesis that arithmetic reduces to logic. Okay? He came up with this system. He came up with a language to write in. He came up with his own logic and his own language in which to express that logic, and he did derive all of arithmetic from his logic. The problem was that his logic was inconsistent, okay? That meant that from the basic principles of logic that he assumed, they were called his axioms, right? The axioms of logic, or for him they were basic laws. From them you could derive a contradiction, okay? And you know if you can derive a contradiction, then there's something wrong, right? And the guy who found the contradiction in Frege's system was a guy named Bertrand Russell. Have you heard of Bertrand Russell before? Okay. Did you know that this is what made Bertrand Russell famous worldwide? Okay, he was a philosopher, but in the beginning of his career, he was a mathematician. And he became obsessed with the same question that Frege was obsessed with. Why is mathematics true? How can I show that mathematics is true? He started doing the same project, and then he found out about Frege's work. He started looking at Frege's system, and then he realized that he could derive a contradiction from Frege's system. I'm going to try to show you the contradiction. It's called Russell's paradox. Has anyone heard of it? Oh, okay. Well, what's Russell's paradox? Someone tell me what Russell's paradox is. Anyone? Okay, I'll try it, okay? So, are you familiar with the concept of a set? A set, a mathematical set, right? Like the set, it doesn't have to be just mathematics, but it can be like the set of all integers, of all numbers, or the set of all points between 0 and 1 on the number line. Basically anything that you think of, there's a set that contains those things, okay? So it's just a way of, as it were, formalizing our talk of objects. Now everything is sets. So what are numbers? Well, they're just sets. What are, these other, like what are points? What are circles? What are squares? They're just sets of points or lines or whatever. So set theory, or at the time it was known as the theory of classes. Classes are just sets. It's just a different word for the same idea. That was built into Frege's system. Okay, so Frege, as part of his logic, he also assumed the theory of sets in a naive form. Naive because it contained a contradiction. So Russell was thinking really hard about the principles that governed sets in Frege's system, and he realized that you could form the set. Okay, well, let me start by saying this. Some sets contain themselves as their own members, right? For example, if there is a set of all sets, okay, the set of all sets, that itself is a set, right? So that set contains itself as a member, right? Okay. It would be an infinite set too, okay? Now, if there are sets that do contain themselves, there are also sets that do not contain themselves, right? Like the set of all numbers between 0 and 1. That set is not itself a number between 0 and 1. So that set does not contain itself, okay? Now, here's where it gets hard. You're like, it's already been hard for the last 20 minutes, dude. Here's where it gets hard. We have sets that contain themselves. We have sets that do not contain themselves. Russell thought there is a set of all sets that do not contain themselves, okay? So think about all the sets that do not contain themselves. Now there's a set of all those sets. Collect all those things, put them in one big set. Now ask about this set. Let's call it R, okay, for Russell. So this set is called R. It's the set of all sets that do not contain themselves. Now, of R, does R contain itself? Okay, it would be really helpful if I had a whiteboard to draw on to show this. But I'm just going to run through the argument, and there's many resources to look it up later if you want to follow this logic. But turns out, if you say yes, then you get a contradiction, and if you say no, you get a contradiction. So either way, you get a contradiction. So let's try it. So, does R contain itself? Okay, let's try first. Yes, R contains itself. Okay? So then R, which is the set of all sets that do not contain themselves, does not contain itself. But that makes it a member of the set. So then it can't contain itself, right? And you go the other way. Okay, so it doesn't contain itself. But if R doesn't contain itself, then it's a set which doesn't contain itself. So it belongs in itself. So it does contain itself, right? So this is called Russell's paradox. Russell discovered this in 1901 or 1902. I think 1902. Frege had been just going on, doing his thing. You know, he didn't realize he had this problem. Russell wrote to him right as his new book was hitting the press. It was getting printed. Frege realized that his whole program was wrong. It was based on something that had to be fundamentally wrong with the very basic insight. So he had to run to the printing press and put a new page in at the very beginning saying, "I'm sorry, but everything in this book is wrong." Right? He wrote back to Russell and he basically said, "That really caught me off guard, and thanks for writing to me." And you know, he tries to figure out a solution and he thought he could figure it out, but he ended up dying thinking that his entire project has failed. Okay? He's a failure. But don't feel too bad for him, because later in his life, he kept journals, and this is in the 1920s. He became a member of the early nationalistic German party, so he started sympathizing with Nazism and stuff. So don't feel bad for him, okay? Even, you know this classic story, all the smart people are always evil or whatever. He's not a nice guy in the long run, but yeah. So Russell finds this problem and then begins a new problem, or a new program, which is, the naive theory of sets, and according to which anything that you can think of can be put into a set, that's got to be wrong. Okay? It seemed really simple, it seemed like it worked, but it's contradictory. So what happened is they came up with a new, less naive and more formal theory of sets, which governed exactly what could be a set and what couldn't be a set. And so it blocks the set R from existing. So in set theory today, you can't derive R. You can't show that it is a set. It's not one, okay? So in other words, sets just can't contain themselves. That's one way of putting it, okay? So where do we stand with the logicist thesis now? The thesis that arithmetic reduces to logic, okay? So Frege thought that it was really important that you start with these very obvious truths, and that's what made mathematics a priori and analytic, that they had to start from these really obvious truths. But once you start changing the truths, such as these truths about sets, and start making it really complicated, it no longer seems like we just know that independent of experience, or know that it's true based virtually, just in virtue of its meaning. So now, to defend the logicist thesis, to say that mathematics does reduce to logic, you have to do some very hard philosophical work. You have to look at the truths of logic, and you have to say, yes, this is true because of whatever reasons, and you have to sort of defend it, and it's not obvious anymore. There's been a lot more work and a lot more really significant results that bear on this topic. For example, have you heard of Gödel and his theorem, the incompleteness theorem? Gödel's incompleteness theorem? Okay. Well, it's another result which is very important for this area in mathematical logic. Anyway, what I do at my department is partly mathematical logic. So I research this topic, and we look at these systems of set theory, or these systems of logics. We look at logics, and we see how much mathematics can you derive from it. How does that work? How do the proofs go? So this is the kind of thing that mathematical philosophers and mathematical logicians care about, okay? We like it because it has this really important final goal, which is we want to make sense of mathematics. We want to show that this thing that we take to be timelessly true really is true, and we want to be able to say why. But it's just not as simple as pointing to logic, saying that we can get it from logic, and saying that's why. Instead, we have to look at these complicated systems, and we have to give really we have to give really detailed explanations of what's going on in the derivations and in the truths themselves. So that's just a brief introduction to the kind of work that goes on in certain philosophy departments and in mathematics departments where I study, and the kind of work that I care about. So I would love to answer any questions you guys have about this stuff, not just about philosophy of mathematics, but about philosophy generally, or about just mathematics. Anything you want to talk about, I'd be happy to answer now. So thank you. Yes?
What is ZFC? It is called Jarmalo-Frankel set theory, but what is the C in this ZFC?
Oh, good.
Is it related with Barton Russell?
It's the axiom of choice. The axiom of choice, okay? So, I didn't mention this, but when I said that we have a new set theory that's more complicated, it's developed by these guys named Zermelo and Frankel. And so, they came up with their first theory, and then they realized that you needed to add one more axiom to the theory, and that was the axiom of choice. So it's C for choice, okay? So it's two guys, and then just the name of one of the axioms, right, is ZFC. Good, I'm glad you know about ZFC already. So nowadays, a lot of the questions, so ZFC is orthodox. It's everyone who's a mathematician learns ZFC, learns how to work in it. And so some of the questions that have been asked now move to the questions about the axioms of set theory. Are those analytic truths? How do we know those are true? So the question gets pushed back to there. Yeah. Any other questions?
So what are the major philosophical debates out there?
Yeah, what kind of things do we still argue about? So logicism isn't the only theory about how mathematics is true, okay? I mentioned Plato's theory that mathematics exists or is true because of these entities. So it's not usually thought now that Plato was right, that there's this other realm in which that makes mathematics true, but people still will sometimes be what's known as Platonists about mathematics. They say that mathematical objects exist, and they exist in a substantial way. I don't know exactly what to make of that. That's kind of the fun, is trying to say what that means without appealing to this other universe or whatever. But you can say that, so there is a debate between Platonists and Logicists. Logicists generally don't want to say that mathematical objects exist in this full-blooded sense. They want to say that, no, mathematical truths are just logical truths, and logic doesn't have objects. So there's a debate over whether Platonism is right or Logicism is right. That's one kind of debate. But there are also more specific debates within each of these traditions in the philosophy of mathematics. So within Logicism, here's an example. When Frege, the guy I was talking about before, when he derived arithmetic from logic, he appealed to his theory of sets, which was encapsulated in this law called Basic Law 5. That was the axiom that proved to be problematic, okay? But you can take a weaker statement that's not Basic Law 5, but it's called Hume's principle. And from Hume's principle, plus the rest of his system, you can derive arithmetic. No problem. You can do it. Now the question becomes, is Hume's principle analytic? Is Hume's principle truly logic? If it is logic, then logicism seems to work. But people will say, no, that's not logic. That's something more than logic. You can't just suppose it and get the result you want. So that's a kind of debate that's been happening. People still look at other variants and what exactly you have to assume. in order to get it, and then they'll argue about whether it counts as logicism or not. Yeah.